Okay, we are back. Please turn to page 3. We're going to do number 5. We didn't finish this problem in any of the classes. You could probably figure this out yourself, but in case not, we'll just talk it out, and then the rest of these should flow pretty smoothly. Well, this looks really hard, but actually it's like not that hard. Let's talk about the setup, which is, I guess, the whole important part of this. How do I want to split this up now? Well, again, when I look at this, I see that I have a single linear factor, and then I have this quadratic, x squared plus 3, which of course can't be factored, so that's an irreducible quadratic. But I have it repeated twice. And it's kind of subtle to understand what the best approach is with such a quadratic. So for starters, let's not do anything particularly fancy. And we'll just pretend that this is some quartic. In other words, let's split this up into some number of x minus 1s plus some number of, and now I'm just going to multiply out this x squared plus 3 squared, which will give me x to the 4th plus 6x squared plus 9. Okay, and following up on our previous conversations, that means that this numerator has to be a degree less, so we will let it be possibly just, so it has to be just a number, and the numerator of this rational expression must also be a degree less, and so we have to allow for it to be a cubic at most, and so we'll write this as bx cubed plus cx squared plus dx plus e. And we know it can't be of degree 4 or higher, because if so, we could do polynomial long division. And clearly we can't be allowed to do polynomial long division because we would get constants, and there are no constants over here. This is a 4th degree polynomial over a 5th degree polynomial. Okay, so once we understand the setup, now we just have to do it. All right, and I don't know, maybe this is kind of hard. I don't know, let's see what happens. I think I picked some nice numbers, so hopefully it's not too bad. So I'm going to multiply through by these two denominators. And I'll get here a times x to the 4th plus 6x squared plus 9. Sure. And here I'll get x minus 1 times bx cubed plus cx squared plus dx plus e. Okay, and now I just need to find out what a, b, c, d, and e are. Well, let's see. If I try maybe x equals 1 first, what happens? On the left, I'm going to get, oh man, I guess that's 65, 5 is 70 minus 7. So that's 63. On the right-hand side, this is going to, when I plug in 1, it's all going to die, and I will get 9, 7 is 16. That can't be right. Oh boy. Let's try this one more time. X squared minus x cubed plus 30x squared minus 6x plus 35. So if I plug in 1, I'm gonna get, oh, I just made a small mistake. 65 and 6 is 71 minus 7 is 64. All right, that is making me much happier, because now when I plug in 1 here, it's going to be 16, and so a is 4. Okay, great. What else can I do? Not much. Let's see, I can look at the x to the 4th term. It's clearly 6 over here on the left, and on the right it's going to be a. And if I were to multiply that all that out, the quartic term would be b. So this is a plus b. Okay, and I know that a is 4, so that means that b has to be 2. All right, and I think that just about ends my ability to do this quickly. I think, and I actually did this problem out. 1 second. Or at least I kind of did. So let me just take a peek to make sure there's some faster way. Yeah, maybe there is. Let's see, what's the, oh yeah, there kind of is, because it's not obvious, but you sort of can do this in your head, because what's the cubic term? Well, here there's going to be no cubic term. Over here, there's only 2 ways to get a cubic term. It's when I multiply x by the quadratic and when I multiply -1 by the cubic. So, okay, it's a little fancy, but the cubic term on the left, its coefficient is -1, but on the right, it's going to be c minus b. Let me just double check that. Yeah, that's true. And that's nice because I know that b is 2, so -2. So actually, c is just 1. Yeah. How about a quadratic term? What is my quadratic term? On the left, it's 30. On the right, it's going to be 6a. And then what am I going to get a quadratic term here? 2 times. When I multiply x by d, x. So that's plus d. And the other time I get an x squared term is when I multiply -1 by cx squared, so minus c. And, okay, I already know that a is 4, so that's 24. D is the one I don't know yet, but c is 1, so that's 6 and 7, so d is 7. Okay, and now, all right, running out of space, let me just skip up here a little bit. What else? I guess I need maybe I can just plug in x equals 0 now. Yeah, let's do that. If I plug in x equals 0, on the left I get 35, the constant term is 35, and on the right, when I plug everything in for 0, for x, I get 9a, and minus e. Okay, and a is 36, so that's 35 equals 36 minus e, so e is just 1. Alright, that was really annoying, but we were successful. And what I can now tell you is that, well, here's what I can tell you. This thing is 4 over x minus 1 plus 2x cubed plus x squared plus 7x plus 1 over this x squared plus 3 squared. Okay, and now we're going to have a repeat of the conversation we had in class, and that is that this is technically correct. This is right. All this algebra we did was correct, and this answer is correct. But even though this is correct, it's not what we actually want. And what we actually want when we do partial fractions is to split up this rational function kind of like as much as we can. To split it up into as many sort of small pieces as we possibly can. And here, it's possible with this part here in purple to do more things with this and make it simpler. In particular, and this is sort of my kind of innovation in teaching this, we can think of this 2x cubed plus x squared plus 7x plus 1 as being divided by x squared plus 3 once, and then being divided by x squared plus 3 like second time. And this numerator here can be simplified because it is a cubic over a quadratic, and so we can do polynomial long division. So over here now, let me just do that polynomial long division. So it's 2x cubed plus x squared plus 7x plus 1 divided by x squared plus 3. How many times is that going to go in? Let's check it out. I guess it will be 2x, and then I get 2x cubed plus 6x, and we end up with x squared plus x plus 1, and that goes in once, and so we get x squared plus 3, and so that's just x minus 2. Therefore, this entire thing here can be rewritten, let's kind of put that off to the side, as 2x plus 1 plus my remainder is x minus 2 over x squared plus 3. But all of that is, of course, still over x squared plus 3. And so I've just replaced what was in red parentheses with the other expression in red parentheses. But now, of course, this numerator can be split up into two terms, and so what we eventually end up with here is 2x plus 1 over x squared plus 3 plus x minus 2 over x squared plus 3 over x squared plus 3. So x squared plus 3 squared. And then we still have this free-floating 4 over x minus 1. Okay, and this answer, which I will now put in blue, is, and I'm just sort of saying this, and I want you to believe it and accept it, better than this expression that we had over here. It's better because it's more broken up into little tiny pieces. The whole kind of idea of partial fractions is, let's take a rational function and split it up and split it up and split it up into as many small pieces as we can, so that it's easier to work with. And this is just more split up, and so we like this better. But then the sort of idea here that's kind of complicated and hard to understand is that when I have this quadratic, which is being squared down here in the denominator, it means that, that this thing that happened to me is always going to happen. That, that after I do the partial fractions the sort of long way, not making use of the fact that this actually is a perfect square, and just treat it like any old quartic, what I'm going to get in general is like a cubic over that quartic. But that cubic is always, over that quartic, is always simplifiable more by kind of dividing through by the quadratic once and then again. And this this is the remainder that you get, this 2x plus 1, is what happens when you divide by x squared plus 3 once. And this x minus 2 is that remainder, which just sort of sits there the whole time. In other words, you can expect that this is always going to happen. And since this is always going to happen, knowing what we do now, we should never do this again. Knowing what we do now, in the future, we should always do the following. Given this exact same problem, where you have some stuff over x minus 1 squared, or sorry, x minus 1 x squared plus 3 squared, we should just, expecting this result, we should just write this as some number of x minus 1s plus some number of x squared plus 3s plus some number of x squared plus 3 squared. And this is, I think, pretty clear to see, is going to be a number, and this is going to be some linear function, and this is also going to be some linear function. If you set it up this way, the algebra will be a lot easier, and you will end up with what's here in the blue. And so in the future, you should do it like that. Okay, make sense?
Yeah.
Good. The last thing to wrap this all up is a test. This is in the bottom of page 3. A little test to see if you get it. Let me erase all of this, or most of it, and just make this sort of fake problem, which is obnoxiously long, but it's a fake problem. We're not actually going to do it. We're going to actually just set it up, because these problems are really all just like, if you understand the setup, then the rest is just doing it. So imagine you had some partial fractions problem, which was x minus 3 times x plus 4 squared, so a linear factor squared, and maybe even another linear factor cubed, and then some quadratic factor, like x squared plus 4 squared, and you wanted to set this up, what would you do? Well, you would set it up as, hopefully, some number of x minus 3's plus some number of x plus 4's plus the like kind of remainder left over, if you're thinking about it my way. And this will be a number, which is not so obvious, but follows from what we did in class and what we just did. And then if you have x minus 5 cubed, by a similar process, you can split that up into the sort of, I'll just write it and hope you just get it, into like 3 pieces. And so this would be D, E, F. And finally, x squared plus 4, that's there in a twice. And so we're going to have some number of x squared plus 4's and some number of x squared plus 4 squared. And so this will be like g x plus h, and this, hope I'm counting right, a, b, c, d, e, f, g, h, i, x plus j, or something like that. All right, that would be the correct setup to some hypothetical partial fractions problem with that as the denominator. All right, if you totally understand that, great. If you mostly understand it, the thing to do is to do all the problems right. In other words, just do this, man. And that's what our textbook tells you to do as well. And then you can continue to ask more questions about the why. But first, let's just start just doing it right. All right, good. You guys are going to watch this video over the weekend and finish the packet. Goodbye.